Alrighty, today we're going to talk about the roller coaster problem. And as you all know, I gave you homework, and I'm pretty sure I'm spelling roller coaster wrong, but it may be right. I don't really know, and I don't care. Roller coaster. Can you guys see my screen? Is the word roller coaster on it? Is there a smiley face on it? I just want to let you guys know you're already better than all of my C classes today. My C classes were just horrible. Horrible. They were no fun at all. Like, first, a third of the kids didn't show up for any of them, which is weird. I got 32 of you guys here, so we got the full class, but it was just unusual. And they didn't talk, and they didn't put their cameras on. It was like, I was very disappointed in all of them, and I told them so too. So I had to change the passwords to something simpler because they were complaining that me using misspelled words was not working for them. So we're back to like just numbers, something boring. So that's all you're going to get. They were really, really whiny. And I don't want to make this any harder than it already is. So we're going to talk about the roller coaster question. And there's a couple of things that I want to remind you about the roller coaster question that all have to come together for the roller coaster question. First, it is definitely a textbook conversation about conservation of energy. It's also uniform circular motion. It's also Newton's laws. It is all of these things. And that's what makes these problems both entertaining but also somewhat challenging. So there's a variety of problems that are related to the roller coaster question that aren't the roller coaster question, but they lead to the roller coaster question. So the first thing I want to promote here is that when we're dealing with the roller coaster question, we are bringing together a lot of disparate parts of what we've done all throughout the year. And, you really want to make it interesting. You change the roller coaster question by changing it from a car to a ball that's rolling. And then you can also get all the angular stuff at the same time. So please be aware that there's a lot of versions of the roller coaster question, and they can get pretty darn complicated if you're not careful. So we're going to be a little bit careful, but I've posted your homework. Please make sure you're working on it. If you think it's going to take you longer than the time I've given, just tell me. I don't have a good gauge for how long the homework takes. My expectation is I'm still giving you about an hour and a half of work per week. It's not always homework. So like if we're doing class stuff or if you're doing something that's due for a class like the FRQ or something, I count that. So if you think the homework's going to take you much longer than that, please let me know. I definitely assigned too much in my mechanics class and had to change the due date. So I want to be flexible. So when we start with the roller coaster question, I want to first start with a question that's like the roller coaster question, but simpler, okay? And that question looks like this. I want you to imagine that I have a box attached to a string, like this. And the string is, say, let's go with 1.2 meters long. And maybe the box weighs half a kilogram. Okay? And I'm just going to let it go. But right now I've got it pulled perfectly sideways, and I'm going to let it go. Now, I don't think this is too hard to grasp, but when I let it go, it's going to kind of spin until it reaches the bottom, where down here, it's going to have some velocity. Does that make sense? The question that I would ask is, what is the tension in the cable when it makes it to the very bottom? It's not an unusual question. It's a very standard question. But the thing about this question that students find challenging is they often don't know where to begin. And sometimes where they think they need to go for a question like this isn't necessarily what they need to do. So in a question like this, I tend to encourage students to consider, what is the problem really trying to get at? And anytime you see an object traveling in a circle, you should probably get your hackles up and be concerned, because something traveling in a circle is a physics test writer's way of seeing if you're really paying close attention to what's happening. They want you to realize, is the circular part of this problem actually important? They want to know ahead of time before they actually start letting you, work on it. So first, is the circular part of this motion important to this problem? For those of you who nodded yes, good job, because it is. It's critical to this problem. Because when I look to this part of the problem, the thing that is pointed out to me more than anything else is that the only way this object travels in a circle is if the net force is unbalanced. That's the only way something travels in a circle. So the first thing I want to make sure that we emphasize in our notes is that if you see an object traveling in a circle, there needs to be an unbalanced force acting on it. So if they're going to ask about force, know from the beginning that you've got an unbalanced force. But it's more than that. If you see an object traveling in a circle, there's got to be an unbalanced force. That unbalanced force has to point, bless you. Somebody just sneezed. I saw it in the screen. They sneezed all over their microphone too. No, they didn't. They turned their head and put it inside their armpit or their elbow or something. But I just want you to know, bless you. I notice things. So you doing all right? It's not the Rona, is it? Good, because sneezing is not one of the symptoms. But I tell you what, when I'm at the grocery store and somebody starts sneezing, I go to the other side of the store. I don't care if it's not one of the symbols or not. I'm not going to chance it. My mom made me a Star Wars mask. I have a Star Wars mask. Yep, Star Wars mask. Because the first one she made me had flowers all over it. And I really didn't care. I'm wearing a face mask. Do I care if it has flowers on it? Not really. But somebody treated me weird at a store once because I had a flower mask on. So I went to Star Wars. So I have a Star Wars mask now. Joey's has flowers on it. Good. I'm with you, Joey. My flower one is in one car, sitting in the dashboard, letting the sun just burn away all the Rona on it. I want all that Rona gone. So, all right, anyways, back to work. If you see something traveling in a circle, there has to be an unbalanced force. It has to be towards the center of motion. That's the thing. Now, there could be more than one force acting on the system, but one of them has to be bigger than all the rest and has to point towards the center of motion. So, in this problem, I recognize that there are two forces that must be acting on the object when it makes it to the bottom. And those two forces have to be the tension and the weight. It should be clear to you that it's going to take more tension to hold the object through the bottom of this turn than if it wasn't moving, because you have to be able to pull up on it in order for it to keep traveling in the circle. So this is where these problems begin, this idea that there's going to be an unbalanced force and that force is going to be related to how fast it's going. This is what really makes these problems, a signature part of what we need to do. And I want to be very clear about it. We can't solve this problem without looking at all the pieces. Like just looking at it right now, we want the tension, but there will be no way of getting the tension without figuring out how fast it's going. And there's not going to be any way to get how fast it's going without knowing about the energy part of this problem. That's what connects these problems together. That's what makes them a little bit complicated, is you having to figure out what it's going to take to drill down to what they're asking. So for this question has to be solved in 3 parts. Conservation of energy to get the velocity, net force to decide which forces are acting in the system, and substitution for uniform circular motion with the centripetal acceleration. 3 parts. So, working this problem out isn't so bad now. I think we've got a good jump on what needs to be done. But just to make sure we're all on the same page, I would probably remind you that there is gravitational potential energy here. It's going to equal mgh. And can somebody out there give me a yes or no? Yes, I've given you the height. No, I haven't. Just put it in the participant window. This lets me know which of you 32 people, you 32 Zooligans are paying attention. I could say them one more time. And the velocity by looking at conservation of energy. That's the first thing that you should notice. We're only going to be able to determine the force by looking at Newton's second law and net force. But what brings those things together is the recognition that this is a centripetal acceleration problem. So our unbalanced force is related to the velocity. Those are the three things that come together in this problem. So you guys all realize that the change in height of the object is the same as the length of the string, 1.2 meters. With that change in height, we should be able to see that at the bottom we're going to have all kinetic energy, which means 1/2 mv squared. So us saying mgh equals 1/2 mv squared should get us to the heart of the question. Now, you guys are pretty sharp, but sometimes your desire to get the answer right sometimes means you look past ways that you can save yourself time. Remember, the exam is going to be about time and efficiency as much as it's going to be about content. And you might solve for the velocity, but that really is taking it too long. You don't need to solve for the velocity. You need to solve for mv squared over r, which, by the way, that exists here. If you look closely at this, you could multiply both sides by 2 and divide both sides by h, and recognize that this and this are the same thing. That saves you lots of time in the long run. Because if you realize that those two things are the same, then solving this problem actually works out to be better if you're using algebra, because I get to say that t minus mg equals 2mg. That's certainly a lot easier than solving for the velocity and then plugging the velocity back in just to get that it's going to be 2mg in the end. Which means the actual answer for the tension is 3mg. And I'm not sure that you would see fit to do that. But at this point, it might be better to work with variables longer than you normally would, because you might see these kinds of connections. So there's the obvious one that I think you're expecting me to draw. So let's put the screen up. There's the one that's going to have what I think are the obvious notes you would expect in this problem, which there's going to be some kind of baseline. There's going to be a starter hill. And there's going to be a loop. And if you've looked in your homework, you realize I've given you several questions that have something like this on it. And the idea is that our car is placed somewhere on the top. It's going to travel through the roller coaster, and we are probably going to be asked questions about its ability to make it through the loop. That's a very standard question. And, there's going to be things about the loop that should be clear to you. The first is that the car's height here is 2r above the ground, but r is the radius of our circle. There's this idea that the car is going to start with some initial height, and then recognition that this problem has all the same kinds of hallmarks as the problem we just did with the string. But there's also another version of this problem. One that used to be at Busch Gardens, but now has been replaced with the iron gwazi which won't open on time, and I'm very sad about that. Have you seen, anybody driven down there to see it? I was down there, I haven't been down there for like 5 weeks, but the last time I was down there, I was on my way to USF, and that thing looks like it's going to be scary. It looks awesome. And because the first initial, one of the drops does something like this, where it's inverted a small amount. It's more than 90 degrees. So I'm very excited. It's going to be incredible. Or it's going to end up being lame like SheiKra was when it first opened. So who knows? Could be either one. But anyways, getting back to work here. The other version of this problem isn't a loop, but is what original coasters used to be, where they have a hill like this, and the hill has some radius. Similar kind of question, but these problems, they're going to be asking about being on top or the peak part of the hill. These are two separate kinds of questions, but they are incredibly related in what has to happen for you to solve them. Generally, both of these problems have conservation of energy. It's a big part of these problems. And generally, we're not interested in how fast the object's traveling at the bottom of the track. We tend to be interested in the speed of the cars at specific points. That point and that point. Those tend to be places where we are very interested in the speed of the cars. The next thing about these problems is there is going to be some form, clearly, of uniform circular motion. Right? We are seeing that there's got to be some kind of centripetal force there and there. In order for the object to travel in a circular path, there has to be an unbalanced force that acts towards the center of the circle. So for both of these, there needs to be an unbalanced force in that direction. Now here's the tricky part. Often these problems are written as conditional problems. And if you don't understand what I mean by the word condition, is they are often described based on what condition must exist for the car to successfully make it past a point in the problem. For example, the car has to have a certain speed, or it won't successfully make it to the top of that loop and won't successfully stay in uniform circular motion. Generally, that means it has to be dropped from a height high enough to provide that speed. So the condition tends to be what is the slowest that it can travel and still successfully make it through the turn. In contrast, there's a similar conditional for this problem. Generally, if the car goes too fast, it will jump off the track. So the question there usually is, what is the fastest the car can go and still stay in contact with the track? In all of these questions, the roller coaster question is almost always at its heart about normal force. Normal force provides the condition. And what that means is, in these problems, the car only stays on the track if it's experiencing a normal force, because a normal force is a responding force. It provides the condition. The limit, this is the banner piece, because we are into the countdown for when Zoom's going to expire. So this is where I have to make my point. The normal force is the condition, and the limit in both of these problems is when the normal force goes to zero. Those are the limits. That means that as your velocity in this problem, as your velocity gets slower and slower and slower, it is the normal force that gets reduced, not the weight. There are only two forces acting on the car at the top: the car's weight and the normal force from the track. Those are the two forces that contribute to the object successfully making it through the turn. The fact that there are two forces here means that these two forces contribute to the net force causing centripetal motion. So when I consider those two forces and the fact that they act in the same direction, I realize that as v gets smaller, that's the right side. So as the velocity of the car gets smaller, because nothing else is going to get smaller about the car. The mass doesn't get smaller. Whatever mass the car has is what the car has. The radius of the loop doesn't get smaller. You've already built your roller coaster. So as v gets smaller, the only other thing that can get smaller is the normal force. What's the limit? When the normal force disappears. That's the limit. I can always go faster than that because the track is there. Can't go slower than that because when the normal force disappears, the car loses contact with the track, which you're going to get to see in glorious slow motion when I post the video. On the other hand, on the other side, there's two forces in opposition. The normal force is upwards here, and the weight is downwards. When I consider my net force over here equals ma, the important difference here is that mg acts towards the center of the circle. I make it positive. Minus the normal force, which acts upwards, equals mv squared over r. So again, I can control how fast the car is going. I can decide where to start the car on the track. But here, that negative sign makes a big difference. Meaning, if I make the velocity slower and slower and slower, no trouble, the car can just sit there. But as I make the car go faster and faster and faster, as it goes faster, the normal force is going to start to disappear. When the normal force disappears, the car's in the air, representing a max speed then. So these problems are limits. They have conditions that are placed on the problem. It's your responsibility going into the exam to know about these conditions. Okay, that's a lot.